This video goes over the binomial distribution, some key characteristics, and a few examples of how to apply it. So first of all, the essential elements of a binomial distribution are there's a fixed number of trials. Each trial has only two possible outcomes, a success or a failure. The probability of success is constant from trial to trial, and the trials are independent of each other. The outcomes of a binomial experiment and their corresponding probabilities are called a binomial distribution. So we can represent a binomial distribution like this. We can also represent it as seen here as the number of successes that we want, the number of trials, and then the probability of success. So if x is binomially distributed, then the probability of obtaining k successes out of n independent trials, when p is the probability of success for each trial, is given by this expression below. So n choose k, the probability of success raised to the exponent k, the number of successes that you want, times q, the probability of failure, raised to the number of failures that you're going to have in your setup of the experiment. So q is equal to 1 minus p. And let's look at a few examples of how to apply the binomial distribution. So in this first example, a fair die is cast 4 times. That is our n value. That is the number of trials. What we are going to do is compute the probability of obtaining exactly 1/6. So that is our k value. That is how many successes that we want in the 4 throws. So the last thing that we need to know is our p value, the probability of throwing a 6 on 1 dice, and our probability is 1 out of 6. That gives our q value as 5 out of 6. So let's write out our formula here so that we can calculate that probability. We have a binomial distribution. The number of successes that we want is 1. Our number of trials is 4, and our probability of success is 1/6. That's going to translate into our formula as n choose k times our probability of success raised to the number of successes times our probability of failure raised to the number of failures, or n minus k. When we evaluate all this on our calculator, we are going to get approximately 0.386. Remember, if you don't have the choose function on your calculator and you're using factorials, we used this notation before. So 4 choose 1 is equal to 4 factorial over 1 factorial times 4 minus 1 factorial, okay? So let's look at another example here. The probability that I get a bus to work on any morning is 0.4. What is the probability that in a working week of 5 days, I will get a bus only twice? So the first thing I'm given in the question is my p value, my probability of success. That also tells me my q value is 0.6. I'm looking for the probability that in a working week of 5 days, that is my n value, my number of trials, that I will get a bus only twice. So I'm looking for 2 successes, or k equals 2. So now let me write it out. So I'm looking for 2 successes, 5 trials, with a probability of success of 0.4. 5 choose 2 times my probability of success raised to the number of successes that I want times my probability of failure raised to the number of failures that I'm going to have in those 3 trials. So these 2 exponents should always add up to your n value. Evaluating that on your calculator, you should get 0.346, or about a 35% chance. Now we're going to do one more example here, a little bit more complicated because of the language in the question. But we know there is a 10% chance of earning an A in a particular math course. So that is our probability of success, which also tells us our probability of failure, or our Q value. 7 students taking the course are randomly chosen. So that is our N is 7. And the first thing that we're going to do is find the probability that exactly 3 students will not earn an A. So that is 3 failures, which would give us 4 successes. So to write that out, we would have 4 successes, 7 trials, 10% chance of success. Putting that into our formula, we'd have 7 choose 4, 0.1 to the exponent 4, 0.9 to the exponent 3. Before I calculate this, I'm just going to go back again to the language. The question's asking me to find the probability that exactly 3 students will not earn an A. So that puts them in the failure category. That is my exponent that goes over the Q. Because I know I have 7 students, if 3 of them are not earning an A, 4 of them are being successful, they are earning an A. So again, these 2 exponents add up to my total N value. When I evaluate it on my calculator, I get 0.0026. Not a great chance of that happening. In example B here, the language is going to change again, and it says at most 2 of the students will earn an A. So the probability that at most 2 students are going to earn an A is going to be equal to the probability that no students earn an A, plus the probability that 1 student earns an A, plus the probability that 2 students earn an A. We need to consider all 3 of those possibilities. And then we can put all those values into our formula here. So we've got 0 successes, 7 trials, 10% chance of success. In our second one, we've got 1 success, 7 trials, 10% chance of success. And then in our third situation, we've got 2 successes, 7 trials, 10% chance of success. Evaluating this on my calculator is going to work out to, you should get 0.4783 for the first one, 0.3720 for the second one, and then 0.1240 for the third one, giving us a total of about 0.9743, or about 97%, that at most 2 of the students will earn an A. The last one here is asking us to find the expected number of A's, and in a binomial distribution, our expected value is N, our number of trials, times the probability of success. So our expected number of A's is our N, number of students, times our probability of success, which is going to give us 0.7. It's okay that this is not an actually obtainable value. It just tells us approximately where our expected value is going to lie.